So welcome to lecture 24 of MCS 472, a course in industrial mathematics and computation. So the purpose of this lecture is to introduce systems of ordinary differential equations. We have already encountered the pendulum model, which gave rise to two equations, but now we will see that systems arrived not only by rewriting higher order differential equations, but that they arrive on their own. So we start in a very computational manner. So I have a Jupyter notebook with some animations that I will show in the first part. In the second part, we will derive what are systems that are linear. Um, and then in the last part, we will see some models that give rise to nonlinear systems. Okay, so what is our first problem? So it's a model of pursuit, and I will start with the tractrix problem, which is in some sense not a problem of pursuit. We have a tractor and a trailer, so the trailer is attached to the tractor. You can think of an agricultural setting, but you can also think about a toddler that's pulling a string. That string is attached to a toy car. So the toddler runs in a circle, and then what's the path of the toy car? So we will answer, or we will provide a model to answer this question. Okay, so what is given? So this will be a two-dimensional model. So we are thinking in the plane. So we know the path of the tractor, and we want to compute the path of the trailer. So it's important here that we have functions of time, but we will draw a curve in the plane. So we are not having our plots will not be plots where we have a range and then a function in function of this range. No, we will actually plot tuples where the tuples are taken at points in time. Okay, so but most importantly, we have a system. So I will immediately show that this leads very naturally to a system of two first order equations. How come? Well, consider that when the trailer is connected to the tractor, that when the tractor speeds up, that actually also the trailer has to change in speed. So what happens is that the direction, most importantly here, that the change in the position is in the orientation, in the direction of the tractor. So the trailer orients itself in the direction of the tractor. So how do you compute the direction vector? Well, it's the endpoint, which is here the position of the tractor, minus the beginning point, which is here the position of the trailer. So we have the x minus y for both components, that is the direction vector. So the direction vector will actually determine the change in position of the trailer. So that's what we want to compute. Okay, so we have to compute the right hand side vector. We have this alpha there, that was the lambda. So we had that the change in position, or the velocity of the trailer, is proportional to the direction vector. We can compute this by computing the projection of the velocity vector. so onto the direction of the connection between the tractor and the trailer. So there is a rigid fixed bar that is here normalized, and we compute the velocity vector of the tractor onto that bar. So we normalize the direction vector first, so this would be when the trailer is indifferent to the change of velocity of the tractor, but that would then mean that the bar or the connection between tractor and trailer is not fixed, is not rigid. So we have to compute the projection, we have to take into account the velocity of the tractor. So here denoted by this x prime, x1 prime, x2 prime. Okay, so then we have a system of the first order equations. And how do we compute this? We compute the right hand side by normalizing the direction in which the trailer is moving. So at any moment we have the position of both the tractor and the trailer. So we normalize that vector and then we compute the projection. So we also have the velocity vector of the tractor. Okay, let's solve this. So we will be using a numerical solver. So here is the equation for, or the function that defines the tractor in function of time. So we take a simple, one of the most simple, well, there is the line, but let's say that the tractor moves in a circle. So now think about a toddler that runs around in a circle in a room, and then the question is where will the toy car end up? Okay, so the advantage of using the circle and the unit circle is that we have nice explicit formulas. So the x-coordinate behaves like the cosine function in time, and the y-coordinates behaves like the sine function in time. Also, the velocity vector is then immediately obtained by the explicit derivative. Cosine is minus sine, sine has cosine as the derivative. So this function will return the velocity, will return the position of the tractor and the velocity as a fourth tuple at any time. So this is a helper function that we will use then in the definition of the right hand side to define the differential equation that models the movement of the trailer. So here is the trailer. So in the last lecture, or actually in the previous to the last lecture, we introduced the differential equations in Julia. So we have to follow this syntax of the exclamation point, where this is a function that changes its arguments. So the first argument will define what is the derivative, what is the left hand side of the differential equation, so the du, given the current position of the trailer. So then there is the parameter p that we won't be using here, and the independent variable t. So we have our trailer function that calls the tractor. So note that in order to define the right hand side, the trailer must know the current location and the current velocity of the tractor. So here you now see that we are using the time t in the parameter function. So we are evaluating the tractor. So we get the fourth tuple back. We compute the vector, normalize it, compute the square root here, divide by the norm, and then compute the orthogonal, the projection of the velocity vector. So the third and the fourth component, ending both with v from velocity, gives the component of the velocity of the tractor. Okay, so that's it. So that's what we have to do as programmers. Then in calling the solver, we first define the time span, then the initial conditions. So note that the unit circle starts at time equals 0 at the right at the position 1, 0. So the length of the bar that connects the tractor to the trailer will be 1. So we will start at position 2, 0 with our trailer. So the time span and the initial conditions are used then to define the ODE, the ordinary differential equation. We solve it, and then we extract the coordinates for the path of the trailer. So that's the trailer path here. So note that what the solution returned is a matrix with two columns, but for plotting purposes we need to provide an array of tuples. So the trailer path does this, and the uh, tractor path here, so this is a static picture, the tractor path is here simply statically computed. So it's just a circle. So we are, in this sense, just looking at the static picture. So, and it's kind of nice. So this tractrix problem defines a spiral. So if you think about the toddler running in a circle, trailing a toy car attached to a string, then at the end of time, when the toddler is tired, then the toy will end up in the center of the circle. Now this picture is actually not that good. So you see that the differential equation was actually quite easy to solve. Not that many points were needed. But actually the plot, the spiral doesn't look very continuous. And if we ask the solver to save at time step 0.05, then we get a very nice smooth trajectory. Okay, so this is the curve, this is the trajectory, but it's actually much better to look at an animation. So here is the code for the animation. It turns out that there is not that much work that needs to be done to build an animation. So what the key point is that we will take slices of the parts, so segments. So the part of the tractor and the trailer, they are computed once, and then you see that the critical parameter here, I, will run to the length of the path in steps of 10. And that will lead to a sequence of plots that are stored in an animation. So we start by initializing an animation object, and after each plot we store the plot as a frame in the animation. And then to render the animation we make a GIF object from that, introducing the frames per second. Okay, and now I should follow the recommendation of showing the Jupyter notebook. So let's look at this Jupyter notebook. If I can change here to the Jupyter notebook. So let me scroll through this. So we are using differential equations and the plots package. So here is our model again. We are given the coordinates of the tractor and we want the path of the trailer. So in the cells we define here the equation. So let's define the problem. So here is the equation again of the tractor. And to make sure that the tractor function is correct, I evaluated this. So you see at position 0, we start at 1, 0. So at time 0, we start at 1, comma 0, and then we have the upward direction vector. So this is the tangent vector to the circle. And here the plot. So I compute, but to run the circle, we evaluate the function tractor for 0 to 2 pi. So we're thinking geometrically here. So that makes one full loop of the circle. And it's a little bit unfortunate that perhaps I can change this with making the font smaller. Yes, indeed. Okay, so we have the plot here. So this is the circle. Trivial, but if you are implementing, do not omit the checks. So again, when coming from our previous plot, when we solved differential equations, we were computing functions in function of time. So here we are computing trajectories. So here you now see that our tractor path is an array of tuples. And in order to have a nice circle looking like a circle, I picked the aspect ratio equal to 1. Otherwise it will look like an oval. So here is a nice circle. Okay, then we have the function of the trailer. So the documentation specifies the types, the function definition doesn't. An omission that I will try to fix later. So again, we define the function here. I'm a little bit more confident. I didn't test it. So we define, but the test actually comes already here when you define the ODE problem. You see the confirmation of the time span and the initial conditions. So we start at 2, 0. Then we solve the problem and we get a success. Then I compute the trailer path. Actually, the trailer path here is extracting, so perhaps I should have pointed this out. So you see from the output, the solution is a matrix with 2 columns, with in these columns the coordinates of the position of the trailer for the time span. For plotting purposes, we turn this into an array of tuples, extracting the x and the y. Here we have our first plot, which was actually not that smooth, but plausible. Then we solve the ODE problem again, and now ask it to save at 0.4. 0.05 at the time step, and now you see that we have a much longer array. We have 400 elements instead of 39, and that leads to a very smooth trajectory, as we would expect. And now comes the animation. So the reason why I'm actually going to the Jupyter notebook. So what is important here is that now we are thinking in time. So the tractor must have the same coordinates. So when we plotted the circle, I was taking samples between 0 and 2 pi. Now we have a time span that is computed by the ODE solver, and that is returned in this dot t, in this t field. So I'm selecting all times and I'm going to running through the circle again with the tractor function, but now I'm going to make sure that my path for the tractor has exactly as many values, as many points as the path of the trailer. That's important. And then to practice the segmentation of the paths, so I'm taking a slice. So here I'm taking the path halfway. So you can kind of now see already. So if I would, instead of an animation, so I drew the spiral, but is the spiral looks like a plausible thing, but is there still the same distance between the endpoints? And here you can kind of verify this. We have distance 1 when we start, and here it looks as if the distance is still 1. So it looks as if it's not really rigorous, but it's plausible. And you can now see that the tractor has not yet completed one complete rotation, one complete cycle, and you can see that the red trailer path is kind of indeed trailing the tractor. Okay, now let's make the animation. So here you see the code for the animation, and then to render it we make a GIF. So here is the running of the GIF. So I will pause a little bit. So it runs into an infinite loop. So here we are. This is the beginning. And you see now, so this animation could be made more complete if the bar between the endpoint of the tractor, so the red dot is the trajectory of the tractor, and then you have the endpoint of the green curve, which is the endpoint of the trailer. So I could still have a bar between them, and that would then be more convincingly show that indeed this is quite a good model of this tractor trailer problem. Okay, good. So let's continue to the slides, or perhaps I should not continue to the slides and continue with the Jupyter notebook so I have fewer transitions. So what is now our model of pursuit? So that was actually the goal, the first part. So now we consider, instead of a tractor, we have a prey. So the textbook uses a duck, and the predator is a drake. So there is a duck that is happily swimming around in a pond, and then there is a predator that goes after that duck. So the model of the tractrix can be modified by using the speed. So we have already computed the direction of the predator of the trailer to the tractor. So we have already that. What we need to add now is the speed. So here the tractor remains the same, and what I will do is that I will use for the speed the model that has the speed is dependent by a constant times time, and that constant is here the acceleration. So we will have a predator that accelerates to the prey, which is most likely more realistic, and the prey here is, which is unrealistic. The prey doesn't really notice the predator and happily keeps on running in a circle. So we have the same model for the prey. So out of convenience, I'm using here recycling the tractor function. In the right hand side definition, I'm using the parameter, which is the acceleration. So I compute the speed, and in some sense it's a little bit a simpler model, so I don't have to compute this projection. When I normalize the direction, I multiply the normalized direction vector with the speed. So that gives me the right hand side of the predator prey. So in some sense it's a simpler model than the tractrix, but the tractrix there is less that can go wrong because of the fixed direction here. The fixed connection between predator and prey, between tractor and trailer. Here there will be more interesting trajectories following. So I use the same initial conditions but shorter time span. So let's set up the problem. Okay, so I have now, I save again. I want to have a nice smooth picture. I save again every 0.05, and now I have 261 numbers. So I need to compute the path for the tractor again. So because I have a different um, um, length of the path for the predator. So here it is. So here you see the geometry, the static geometry of the path of the prey, the circle, and then the path of the predator is kind of strange with this loop in there. So in order to properly understand this, that this is most likely not a bug, let's look at the animation. So here is the animation. So I should probably point out what did I pick for the acceleration. So for the acceleration, I forgot to mention this. So here this is the last parameter now in the setting up of the ODE. The acceleration is 0.1. Notice that the speed is acceleration times time. So we start at time equals 0. So the initial velocity of the predator is actually very, very slow, whereas the prey moves with velocity 1. So the prey is at velocity 1, and initially the predator is very slowly creeping up on the prey. So here is the trajectory, the static trajectory, and let's now look at the animation. So you can perhaps now thinking about, instead of a drake, think about an alligator, which very, very slowly comes creeping out, and you kind of see that as the um, predator moves towards the prey, it kind of misses this. So at that point, when they almost encounter, when they cross paths, which they actually don't do, except at the very end, when they cross paths, the speed of the predator is still too slow. So, and in some sense, this could be a realistic model. You can kind of see that the model is set up so that indeed already from the beginning the predator follows the prey, but then somehow needs to accelerate. And it catches up. I should actually point out, so this is of course following numerical analysis. If you have taken numerical analysis, you might have wondered ever what happened when the predator catches the prey, because then actually the locations are the same, and if you compute the normalization, you essentially divide by 0. But the entire code system is actually quite robust. So the division by 0, so here we are again at the animation. So you kind of see that the both points, they actually catch up. And if you would run this animation for longer, then both actually continue to go on the circle. Okay, so that's the Jupyter notebook. So let me swap the slides now for, let me move the Jupyter notebook out of the way and go back to the slides. So we'll very briefly scroll through this. So we now know the adjusted tractrix model. So here it's, so I can now point at some alternatives. So the prey moves at a constant speed. One can also build, so the tractrix problem is actually a perpetuum mobile, where the prey and predator, they move at the same speed, so the predator will never catch. So um, if the constant speed is 1, then the predator will never catch the prey. Likewise, if the speed is less than 1, so this could be as a predator giving up, slowing down, but you could have a constant speed that is larger than 1. Now, the second model that was showed is actually much more realistic. So you have a predator at rest and slowly increasing the speed at a constant rate. Um, of course, it would be more interesting if the prey, so they leave it off as an exercise, when the prey would also start to accelerate. Okay, wow, that went fast. So here at the end of the predator prey simulation, so why is the trajectory as it is? So in the very beginning, we have the very slow speed of the predator, but when I took acceleration 0.1, once the time goes past 10, and here is kind of the justification for 13, so 13 at the end of time. So the time really needs to be past 10 for the speed of the predator to go past 1. So after that, eventually the predator catches the prey. Alright, here is another predator-prey model, and in some sense solve this problem at the end of the lecture, so as you always do, because this is already a nonlinear model. So let's denote two populations. So this comes again from mathematical biology, population dynamics. So we have the rabbit population and the foxes population. So if you do not look at the correction term, so the rabbits grow exponentially if there aren't any predators. And foxes, they are meat eaters, they need rabbits. So if there are no rabbits, then there will be exponential decay. So the second term on the right hand side of both equations denotes the encounter between the rabbits and the foxes. So that is proportional to the product of the population sizes. So the coefficient in the first equation for the rabbit population is negative, as mostly an encounter between a rabbit and a fox is not ending well for the rabbit, but it's ending well for the fox. So the fox population increases as a consequence of the encounter with a rabbit. So the exercise is to solve the system of differential equations and plot it. There is an interesting dynamics. So both populations tend to hold each other in equilibrium. If there are too many foxes out there, then the rabbit population starts to decrease, and then the foxes population doesn't have enough food. So there is this kind of pendulum-like mechanism that swings back and forth. So there is a nice periodic motion in this model as well. So the end question here of this exercise: can you find the time at which you have one complete orbit? So there is a cycle in this model where when you start at 3, 2 for the initial conditions, then you end back at 3, 2 for this particular choice of parameters. Okay, so more than half an hour on the first part. So the other part of this lecture, the remaining of this lecture, is less computational. So let's look at the multiple spring mass system. So in 2 lectures ago, in lecture 22, we considered the derivation of the single mass and one spring system. So we have here a mass that is stretched out, so the equilibrium displacement is here at 0. So we have the displacement as the variable. So the spring will restore towards the equilibrium state. We have this model for some constant, so the constant k depends on which spring we are using. And now we are considering, so this is a systems lecture, we are considering multiple masses. So here on the picture I have three masses depicted at equilibrium. So in the middle mass, so the middle mass is connected to two springs, one from the left, so there is a push coming from the first mass, and then a push also coming from the third mass. So these are the positive restoring forces that are coming to play. And then there is the middle term that is related to the displacement of the second mass and the two constants of the two masses. So this gives us the middle equation. So we can generalize this into this system. So this is a system of three second order equations with some spring constants. So this can be written and has to be written if you want to solve this numerically. This has to be written as a system of first order differential equations. So from the starting three equations, you will end up with 6. And write this in matrix format. Okay, so let's look at related model. So we consider, instead of masses, we consider cars, and we consider a platoon of cars. So we have a sequence of cars on a road where we have the position of the first vehicle denoted by x1, and then xk is the position of the kth vehicle in that platoon of cars. Now, what happens as a consequence of a disturbance, say that the first car starts to brake? And in particular, what happens to the distance between the cars? So, will there be a collision, yes or no? So, that's the question that we are trying to ask. So, what is the change in the velocity caused by the change in the velocity? Well, we can write that down. So we have the delta t, which is the reaction time of the following driver. So we have the acceleration. The change in the acceleration depends on the velocity of the car in front of the kth driver. So this is obviously a model for k larger than 1. So there are two parameters in there. So one parameter is the reaction time of the driver, and the other parameter is a sensitivity parameter. So here I give empirical values. So I will later give an interpretation for the alpha parameter. Okay, so this is our model, acceleration and velocity, but we are interested in distance. So note that distance from calculus equals speed multiplied with the time traveled. So the distance between two vehicles, so the current position and the previous position. So now we look into the x-axis, and the so the xk minus 1 is actually more is farther away from the xk, so this is a positive number. So the distance equals speed multiplied by time is expressed here. So we have the distance in time, the ds, multiplied by the distance by the differences in the speeds. And then we have the initial constant. When we do the integration, there's a constant coming in, and that's the initial distance between the vehicles. Okay, so now we derived on the previous slide a model for the change in velocity, the acceleration. So we're going to replace the difference between the two velocities that we derived earlier by this acceleration term. And now when we complete the integration, so the anti-differentiation of the acceleration, then we see that we have a difference in velocities. So difference in the velocity at the reaction time and then at a time 0. Okay, what good does that do to us? Well, we have now a relationship between the distance between the vehicles and their velocities and the initial distance. Okay, let's try to interpret everything. So what do we have? So we have the initial velocity. So let's now assume that the v, when the delta t is small enough, that this is still somehow the same. So we have then what we can derive from this is the condition that at any time there is no collision. So what is the relationship in the initial velocity and the initial distance? So here the v that we abbreviated from the vk at delta t. So we want to, so this has to be positive. So let's just ignore this term here. It could be that the platoon has come to a halt. So, but for the distance to still be larger than 0, we have either a bound on the speed that involves this alpha, or we have a bound on the distance. So we have an upper limit on the speed or a lower bound on the distance. And now we can interpret this alpha constant that gives rise to the 3-second rule. So in this course you will learn how to apply mathematics, but perhaps you will also realize a little bit to become a safe driver. So there is this 3 seconds rule that is derived as follows. We have this lower bound on the distance that you have to maintain between vehicles. And it's kind of logic that as the velocity increases, that the distance should also increase. And here you see this factor 2.7. And here is the 3 seconds rule now, that the distance between two vehicles should be larger than the distance traveled in 3 seconds. So one can, from this rule, also a little bit try to think about the speed limits. Do the speed limits make sense if you take into account this 3 second rule, given the normal traffic flow? Okay, so here is then a proposal for a topic. So in Chicago we have many expressways. An old name for UIC was Chicago Circle Campus. So you can even look from some of our towers and take a video of the traffic. And then you can try to measure at several times of the day what is the separation between the cars, and what is also the separation versus velocity. Um, do you really observe that if there are more cars, if the traffic gets denser, that hopefully also the velocity um, gets smaller? So, and that's the third part. How is flow actually related to density? So, flow meaning the number of cars that pass through. So, when is the road most dangerous? And that's most likely between the transition time. So, not so much perhaps in the rush hour or in the off rush hour, but just in between the daylight when things are starting to speed up or slow down, perhaps speed up. So, this is a nice topic for a project. Alternatively, one can investigate this 3-second rule related to the speed limits. Okay, I have about 4 minutes left for two other models. Here is the model that looks at the administering of half a pill a day. So you have at the beginning of time a bottle of full pills. And what you do each time you take a pill, if it's half a pill, then you just take it. But if the pill is whole, then actually you break the pill in half and then you keep the one half and you throw the other half in the bottle. So the question is then, after a number of days, how many whole pills are left in the bottle? Okay, let's think about this problem by assigning variables. So we have the expected number of whole pills and we have the expected number of half pills. So this is a question that I could have probably also have asked and that you can already solve with Monte Carlo simulation. We will see that the average number of pills, so that might be the final answer that you may be interested in if you run your Monte Carlo simulation, that its average number can just as well be computed as a solution of a differential equation. So that's actually the punchline here. So let me try to derive. So what is the difference now in the number of whole pills? That's actually the negative of the ratio of the whole pills over the total number of pills. So you can kind of see this ratio also kind of as a probability. So what is the probability that you pick a whole pill? And that will be the difference in the number of whole pills. Okay, so then what is the number of half pills? So it's the increase whether there is a whole pill drawn. If a whole pill is drawn, then there is indeed a 1 an extra, but then there is the decrease if actually a half pill is drawn. And these are expectations. So I'm going too fast now because I don't want to drag this lecture on, but we can introduce the expected percentages for some total number of pills. So pk is the expected percentage of whole pills, and the qk is at complement, so the expected number of half pills. Complement at the beginning. Okay, so we can then use this notation. So we had the discrete model for the expected number of pills. This can then be rewritten in terms of these percentages, or if you like, the probabilities. So this is a rewrite, and this rewrite is then not such a big step anymore to a continuous version. So one can still keep this as a discrete system, but you can also formulate from there a continuous version, where you start initially with the percentage of whole pills to be 100%, and then no half pills. So, and this is now a completely deterministic system, which is kind of surprising. So this provide some model for something that looked very probabilistic. So the question in this exercise here, does this model make sense? Okay, I'm running over time. Let me rush through the last model, which is an interesting model that will lead to a system of difference equations. So we are considering an arms race. If two nations battling each other is not such a good time to think about now. You can also consider two companies who have an advertising campaign. So then instead of the arms expenditure, so how much of their budget do they spend on advertising over their total budget? So we have that the companies or the nations, they are reacting um, in reaction to each other. So if you think about companies, we are back into micro or macroeconomics. Um, so also there we introduced already difference models. So in some sense here with this model we loop back to the equilibria uh, situation there. So if here for this concrete model of two equations you look for an equilibrium, you can get to an equilibrium equation if you eliminate. So you can replace here the yn plus 1 by the xn. And then at the fixed point, you replace all the xn's by x, and at the fixed point, xn plus 2 is x as well. So then you see that you get a cubic equation if we divide out the trivial solution. Okay, so then the last question is for the parameters here. I have three different values of the parameters. Compute the number of real roots that you have. So one has either one real root, so this is a cubic equation with real coefficients. Either you have one or three real roots. The one root problem is rather boring. The three roots problem is kind of interesting because one of these equilibria, one of these fixed points is not stable. And you can get into chaotic situations where any state in between is actually possible. So the last case is actually quite interesting. So this is also the case where you see now that the first, so this was really a war that was going on, a marketing war where the first company spent 80% of its budget on advertising, and company B stepped up and started using 90% of its available budget to advertising. Okay, sorry about running over time, but I hope this lecture was quite interesting. So I only worked out one model computationally, so the lecture could have been much, much longer if I had worked out the remaining four models also computationally numerically. So these are left for exercises, and there's one interesting project to this. So as always, we there is the main reference, which is the textbook. So we ended by now the 9th chapter. So I thank you for watching this recording.